Next up, we have the Test of Time Award. And here to present the award and talk a little bit about why this paper was chosen is Arthur Gretton from the Test of Time Award Committee.
So thank you, Hannah. So I'm here to present the Test of Time Award, actually with one of my co-committee members, Csaba, and on behalf of the larger committee. So the award this year goes to the paper, The Tradeoffs of Large-Scale Learning by Léon Bottou, Olivier Bousquet. So it turns out being on the Test of Time Committee is very hard, as I discovered. So we had a month of very vigorous email debate. I think it ran to something like 20, 30 pages. There were so many amazing papers to choose from, and it was a real privilege to reread some of the papers from 10 years ago and to see some of the work done. So we did have an exceptionally tough time choosing among the leading papers. All of them had strength in different areas and an outsized impact in their respective disciplines. So it was a real education to see what had been done. So this brings us to this year's award. So if we rewind to the state of machine learning theory back in 2008, the discussion was about trading off two sources of error: estimation error, which arose from having a limited number of samples, and approximation error, which arose because our learning algorithms were simple in some sense. But as far as solving these learning problems was concerned, as long as you were prepared to solve it in polynomial time, you were good. But then, this is fine if you're in the limited data and unlimited time scenario. In modern machine learning, we have unlimited data, but we have limited time. So what do we do? So in this case, we can't minimize empirical error exactly. We have to minimize it approximately. And that causes a third source of error, this being optimization error. So then how do you trade off now these three sources of error: estimation, approximation, and optimization? So this is where this paper really had the pioneering result. It was the first rigorous analysis of the trade-off of these three sources of error. And one of the results that it showed, which I think is relevant to this day, is that stochastic gradient descent is a good choice in achieving a good balance between these three sources of error in the large sample regime, which is where we live. So this remains a really lively area of research today. Trade-off between optimization, approximation, and estimation is one of the, I think, most necessary and important questions that we should continue to ask ourselves. And this paper really was the first rigorous effort in that direction. It's made a large and lasting impact in the field, and for this reason, we decided to award the Test of Time Award to this paper. So, Olivier, if you can come up.
Working? Yes. All right, good morning, everybody. It's actually very intimidating to be here. The room is getting bigger every year. It's certainly much bigger than it was in 2007. And it's very humbling to receive such an award, and especially knowing how fierce was the competition to be here. And unfortunately, my co-author, Léon Bottou, who is actually the first author of this work, and thus deserves most of the credit, could not make it today. It turns out that in his own words, he said, "I owe more to my family than I owe to my vanity." And certainly, I cannot blame him for getting his priorities right. But in order to take care of his vanity, let me show Léon. So, indeed. So you have me, and I will do my best to represent him, of course. So, as all stories in computer science, at least, they go back all the way to the 50s. And actually, this work, in particular, you can trace its roots to, somewhere around the early 50s, where there was the work of Robbins and Monroe on stochastic gradient descent. But I won't go back all the way to that time. I will start my story in 2003. So 2003, I was organizing this machine learning summer school in Tübingen. And this was the time, if you remember, well, you probably don't remember, because most of you were not there at the time, probably in machine learning at least. So at the time, support vector machines and kernel machines were all the rage. And so Léon came to give a lecture, and surprisingly maybe, or it felt a bit weird at the time, because he was talking about an algorithm that felt a bit outdated. He talked about stochastic gradient descent, and he was advocating using this algorithm in SVM when everyone else was doing quadratic programming and conjugate gradient descent and things like that. So it felt a bit surprising. But he had this very interesting thought experiment. He said, like, imagine that your data set contains lots of examples that are duplicated. Then if you do stochastic gradient descent, that means you process one at a time and you do a gradient step. So even on those duplicated examples, you will make gradient steps, so you will move forward. Whereas if you do batch learning, then you will compute the same gradient many, many times and apply it only once at the end of the batch. So you will waste a lot of computation. And that was his argument for saying that maybe stochastic gradient descent should be considered. He also had this very nice picture that I remember captivated me, and I thought this is really the essence. If you look at the parameter space, when you start at W1 and you do online or stochastic gradient descent, you make these small steps, so you don't make too much progress, but you're constantly going in the direction of the true solution, the solution being the optimal W for the test error. Whereas if you do batch updates, or you do batch gradient descent, let's say, you will make faster progress, but towards a solution which is the best in training error. So either you go straight to the best solution in training error, or you go slowly to the best solution in test error. What should you choose, right? Either you go fast to the solution that is not necessarily the one you want, or slow to the solution you want. And I felt at the time there should be a way to characterize that more formally and to quantify it in particular. He even had this picture that showed that, interestingly, this difference between the best stochastic gradient or the point at which you reach with stochastic gradient and the true error is actually the same distance, roughly speaking, as the difference between the test and training error. And so he concluded his talk, or his lecture, by saying that stochastic algorithm can become attractive in the regime where you have large amounts of data. And that was really, at the time, more an intuition, than a real theorem or something really formal. But then, we both went back to our other projects and kernel machines in particular. And until 2006, where Léon edited this book, Large-Scale Kernel Machines, where it was a bunch of papers about trying to scale up kernel machines to larger data sets. And in there, if you look at the introduction, there was this proposal of a framework for studying the large-scale regime, which was this decomposition that Arthur mentioned in approximation, estimation, and optimization error, and this formulation of the difference between small scale and large scale being that you're limited by the training set size, whereas in the large scale regime, you have lots of data, but you're limited by the computational power available, or the time that you're willing to spend. And more or less at the same time, people were starting to experiment with stochastic gradient again, and in particular in CRFs and in SVMs, and the results were quite surprising. Like, it was going really, really fast compared to the existing algorithms. And so that was it, right? Like, Léon contacted me and said, well, this thing that I was showing in Tübingen, I did remember very precisely this picture. He said, let's make it formal. Let's write a paper about it. And I immediately jumped in, and we wrote this paper in 2007. So this is the abstract. Really what it was is a theoretical paper, right? Like, there was no experiment in the paper. And it was presenting that framework, formalizing it, and analyzing a bunch of algorithms in that framework to show that indeed stochastic gradient descent does an advantage when you take into account this trade-off between optimization and estimation error. And so, what we did in this paper was formalize these different notions, and then take a very simple case, because of course, if you want to analyze properly, you have to start simple. So we, fix the class of function, use a linearly parameterized class of function with a smooth convex loss. Of course, that's very limiting, but we had to start somewhere. And we looked at these 4 different iterative optimization algorithms, both in the stochastic case and the batch case, both first order and second order. And so here's the picture that you get when you do that. If you look at the amount of iterations that you need to perform to reach a certain accuracy in the optimization, what happens is that gradient descent, the first 2 columns, first order and second order gradient descent are really, really fast. It's like log 1 over rho instead of 1 over rho for stochastic gradient descent. So you might think, okay, well, it will take forever for me to reach any correct accuracy for my optimization algorithm. But it turns out that, on the other hand, the iterations themselves are much more costly when you do gradient descent on a batch, because you have to process the whole batch before making one iteration, whereas in SGD, you make a step at every time you look at one example. So if you put those 2 things together, you get a time or complexity to reach a certain accuracy of n log 1 over rho in the gradient case and 1 over rho in the SGD case. But what's interesting is that when you take into account the estimation error, because the point is that there is no point in optimizing all the way to perfect like 0 training error. If you have very limited amount of data, you will have some estimation error that comes from the fact that the training error is not the same as the test error. So you should only optimize to a certain level which corresponds to the size of your estimation error that you cannot beat given the data that you have available. And when you take that into account, what happens is you get this picture where if you compute now not the time it takes to get a certain optimization error, but the time it takes to get a certain overall error, optimization plus estimation and approximation, you will get a picture that looks like this, where SGD now is actually better than gradient descent. Like to get an error of 1 over epsilon, it will take you a time proportional to 1 over epsilon in SGD, whereas in gradient descent, it will be at least a log factor worse and possibly even worse, depending on the assumptions that you make on the noise in particular. But so the point and the conclusion is really that, if you have to remember one thing is that if you have the possibility of doing so, then spend less time on more data. So it's better, to use the time that you have, the computational time, to look at more data and optimize over more data rather than, taking a small subset of the data and optimizing more and more. So this was a theoretical paper, but interestingly, that same year, Léon was asked to give a tutorial at NeurIPS, and initially on these large-scale kernel machines, but he took the opportunity to actually write some code and do some experiments that would complement the paper. So the tutorial ended up being, the presentation of those experiments. And he actually put up this website where you could download the code for doing SGD on CRF and SVMs. And as he was presenting the tutorial in the room, people were trying it on their laptop, and they were amazed that it actually works. And there is this phenomenon that indeed stochastic gradient descent is slower, but it reaches the interesting regime where the optimization error is close to the estimation error much faster than the other techniques that eventually get much faster to get to a very small accuracy, but that's not the point. You don't need to go all the way there. And this is one slide from that tutorial where he was showing experiments on the Reuters data set on text categorization. And you can see that to get the same test error, SGD was taking like orders of magnitudes. It was order of magnitudes faster than any other SVM solver at the time. And so what happened later, after this paper went out, is that first, people tried it again and confirmed the results, like Patrick Hafner, for example, making some experiment of the same nature. Then, for example, Olivier Bousquet, who was quite a big fan of conjugate gradient descent and had a very fast implementation of it, proposed to run batch gradient descent, but with smaller batches. He said, maybe with smaller batches, you get to the same performance as SGD. But turns out that stochastic gradient descent was better for any batch size. There were also like some theoretical follow-ups right afterwards, this paper in particular, where the analysis was refined a little bit to take into account the regularization in SVMs. And then there were essentially three directions in which this was pursued. One was variance reduction. Stochastic gradient descent has this disadvantage that the gradients are noisy because you take randomly a point at every step. So people try to reduce this variance by doing some averaging of the gradients. It worked really well in convex optimization, but it's not clear yet to this point whether it's really useful in the case of deep learning, for example. Another direction was this notion of implicit regularization. That's something that the original paper did not take into account, the fact that if you don't optimize all the way, then you also have some regularization effect by the fact that you don't go to search the whole space of function. And we use like worst case estimation bounds. It turns out that you can potentially get better if you study this property, and that's this notion of implicit regularization. And the third direction is trying to make these algorithms more robust because they are very sensitive to the step size or the learning rate and how you change it over time. So many people have tried to create algorithms that are more robust to this choice of parameters. But really, the paper ended up being this thing, right? Like an excuse for using SGD in some sense. Like people were saying, oh, well, there is this theoretical paper. It proves that SGD is better. Let's just use SGD and forget it. But so, let me give you a few thoughts that are inspired by this story. The first thing I would say is scientific truth doesn't follow fashion. And, you should study SGD even if nobody cares about SGD. And, the worst thing that can happen to us as a community is that we all start working on the same things and we all explore the same ideas. We need diversity, not just in terms of people and cultural backgrounds, but also in terms of ideas. And one way to get to scientific truth is through experiments. And by experiments, I don't mean that table that you put at the end of the paper where you magically found the right setup of the architecture, the parameters, and the data set on which you can do better than the baseline or the state of the art. What I mean by experiments is in the scientific sense of a scientific experiment. Like scientific experiments should help you understand phenomena. You should start with a hypothesis and perform an experiment or a series of experiments to validate or invalidate this hypothesis. And experiments that show that things don't work are just as important and useful as experiments that show that things work. That's something we often forget. And last is on the use of mathematics. Of course, theorems are here to help us understand again. A theorem is not a blank check that, now that there is this theoretical guarantee you can go and use this thing, it's guaranteed to work. That's not the case. We are dealing with data, and there are lots of things that theorems don't capture about our data. And the flip side of that is that we should not just focus our energy on algorithms for which we have theoretical guarantees, right? Like it's perfectly fine to develop an algorithm, prove that it works like with proper experiments, and if you don't have a proof for it, so be it. That's fine. Let's not just, focus on an algorithm for which we can prove something because it limits our creativity. And so, to conclude, I will take this opportunity to present maybe 3 directions of research that I find interesting and promising. The first one is, continuing this line of research on stochastic gradient descent. I think we're still far from understanding all the subtleties of this algorithm, especially when it's combined with deep learning and with these networks that are largely over-parameterized. There are lots of interesting effects that tie the over-parameterization with the stochastic gradient descent to lead to interesting generalization. The second point is I think we are somewhat limited also by this paradigm in which the training data is always like the test data. So the test examples are from the same distribution. But really, if you think about it as humans, we learn to do simple things, and then we are able to perform complex tasks that are compositions of those simple tasks that we have learned. And our models are not designed this way with compositionality in mind, and the same thing for our test data sets or benchmarks. They are not designed with this compositionality in mind. I think this is a direction that we should pursue. And the last one is causality. As humans, we are very good at building causal model of the world by interacting and observing it. And again, our models currently don't have this capability. And I think those two last points are important if we want to build models that we can trust and that we can understand when we apply machine learning. And with that, I would say that Léon and I are really grateful and thankful to the committee for this impressive and humbling recognition of our work. So thank you. Do you have time for questions? So we have time for a few questions. Questions? All right. If no questions, then I guess we'll get to the break. Thank you again.